The Gauss-Jordan method is an extension or improvement upon Gauss's method. Let's see how it works in an example. Here we have a three-equation, three-variable system. And as usual, we're going to clear the first column, working downwards, and then move to the right, clear this column of the entries below leading terms. And so we're moving from left to right and down, top to bottom. And in the Gauss-Jordan method, we're going to do this first and then do something the opposite second. So first you can see that -2 times the first row will clear this term here. -1 times the first row will clear this one, and this is what's done here. And then now we need to clear the -3y from this row, and we can just add minus the second row to the third row, and that clears the -3y in the third row, leaving us with a system in echelon form. Now what we're going to do is we're going to do something new. We're going to use row operations to move the terms above each leading variable, working from right to left and bottom to top. And then we're going to rescale the leading term for each leading variable so that the coefficient is 1. And at that point, we'll be able to just read off the solution. Let's see how it works. Here's the same system. I've just repeated it here. And now we need to start from the right and clear these two terms here, and the -2 times the third row will clear this first term, and then the adding the third row to the second row will clear that z here, and that's what's done here. It only affects the constant terms on the right. Okay, now we have to move from right to left and clear this column here. Let's see how that works. Well, what we can do is we're first going to before we do that, it'll be simpler to get rid of the 3 first here. So we multiply by -1/3 to clear the -3, leaving this 3 here. Then we can add the second row to the first row, and then there you have it. This is called reduced row echelon form, in which each leading row has no entries above or below it, and the coefficient is 1. And that means this is the solution: x equals 1, y equals 3, and z equals 2. The last form of the system, as I said, is called reduced row echelon form. It is the goal of the reduction. The shift from moving from left to right and clearing columns downwards in Gauss's method to moving from right to left and clearing columns upwards is called pivoting. A matrix or linear system is in reduced row echelon form if, in addition to being in echelon form, each leading entry, that is, has to be to the right of the leading entries above it. Each leading entry is a 1 and is also the only non-zero entry in its column. The cost of doing Gauss-Jordan reduction to solve a system is the additional arithmetic. The benefit is that we can just read off the solution set description. Let's see how it works in another case. Here we have 3 equations, but 4 variables. It's a little more complicated, so we'll use the augmented matrix. Here's the linear system. Here's the augmented matrix that represents it. We're just reading off the coefficients and putting in zeros for missing terms. Okay, and so what we're going to first do is we're going to do the same thing, go to echelon, find the echelon form, which means we need to work from top to bottom, from left to right, so we can clear this one here with minus row 1 plus row 2. That only changes this second row here, as you can see. Then it'll be easier to add -2 times the third row to clear this 2 if we swap rows. We swap the rows, then add 2 times, I've repeated this matrix down here for clarity, then I'm going to add 2 times the second row to the third row, which clears the 0 here, so we have it in echelon form. Now, we're going to start the Jordan part of the Gauss-Jordan method and normalize and pivot to clear the terms above the leading variables. Here it's going to be easiest to clear the normalize each row first. So we multiply the second row by -1 instead of -1, 1. -1, we have 1, -1, 1. And we also normalize this last leading term to be 1. So here we have it with all the leading terms normalized to be 1 at the cost of a fraction over here. However, now it's going to be easy to move from right to left to clear the entries above the leading terms. This won't be clear. So we're not clearing everything. We're just clearing the terms above the leading rows. Okay, so how does that work? Well, we're going to add row 3 to row 2. That'll clear this term. And that's what you get here. 1 plus minus 1 is 0. 1/5 plus 5/5 is 6/5. And minus 1/5 plus 0 is minus 1/5. Now we need to clear this minus 1 here because we need to clear all the terms above the leading entries. Okay, I've repeated the matrix here. Here's the 6/5, the minus 1/5. We still need to clear this. And we only have one more row operation. Row 2 plus row 1 will do it. And so that clears this. And this is 6/5 plus 10/5 is minus 4/5. And minus 1/5 plus 10/5 is 9/5. And so now we can just read off the solution. Now, it's a little bit more difficult because we have a free variable. So we have some terms over here, but we're going to be able to see that x is going to equal 9/5. This is going to be, see, x, y, z, w. So it'll be y1 equals 9/5 plus 4/5 w. And this will be 1 equals minus 1/5 minus 6/5 w. And this will be 1 equals minus 1/5 minus 1/5 w. So this records that reading off, in which this is the constant, these are the constant terms, 9/5, minus 1/5, minus 1/5, and 0. It's oftentimes a common error is to see these 3 rows and make this height 3, but there's 4 variables. This is x, y, z, and w. So this is x, y, z, and w. The equation for w, the free variable, is just w equals w. So w doesn't have a constant part. It just equals 1 times w. Okay, so, but then we can read off these 3 as with the sign change of moving to the other side of minus 4/5, 4/5, minus 6/5, and minus 1/5. So we can just read off the solution if we understand what we're doing. Okay, I just repeat the fact this is a common error to leave off this last free variable equation. And that is it. There's more examples in the text.